Hello students, let's begin section 1, Orthogonal Basis. So far we had been studying orthogonality. Now let's apply the orthogonality to basis, and that's called orthogonal basis. Goes like this. A basis v1, v2, v3, v4 all the way over to vn of a scalar product space is called orthogonal if it consists of mutually perpendicular vectors. Here we go. Vi dot vj is equal to 0, consequently vi and vj are perpendicular to each other, whenever I and j are different, that is. Now, on top of that, if each basis vector is a unit vector, that is, it has size 1, then we call it orthonormal basis. Let's see. Ui dot uj is equal to 0 whenever I and j are different, so they are orthogonal to each other. Also, when I and j are the same, then what we get? Ui dot ui is equal to the norm squared, which is 1. Oh, that means ui has norm 1. So it's a unit vector. In that case, we call it orthonormal basis. By the way, this expression, 0 whenever I and j are different, 1 whenever I and j are the same, this whole expression can be abbreviated by this single expression, delta ij, and that's called Kronecker delta. Kronecker delta notation, or just Kronecker delta. And if you want some history behind it, and also about German mathematician of 19th century, Kronecker, and you can read about it in various sources. Go to Wikipedia or something. It's quite useful, so I may use delta ij in various different places. Now, once you have orthogonal basis, it's really easy to make an orthonormal basis out of it, because you can always do this. You can always define ui as 1 over vi times vi like this, whenever we have orthogonal basis. This way you can get a unit vector in the direction of vi, so we get orthonormal basis. So existence of orthogonal basis automatically gives you orthonormal basis. Now, why is this so important? There are many reasons, but here's the first. It is related to calculating the scalar product. Here we go. Let V be a scalar product space, and let U1, U2, U3 all the way over to Un be an orthonormal basis. Now we select a pair of vectors V and W arbitrarily. Then you're going to get the coordinate expressions of V and W with respect to a given basis system, and this is a basis system. Let x and y be those coordinate expressions. Typically, we use column vector expressions, all right? Now, how do we calculate the scalar product v comma w? It'll turn out v comma w is equal to x transpose times y. Now, x and y are column vectors, so x transpose is a row vector. Row vector times column vector, basically we are talking about this. So x transpose is a row vector, and then y is of course column vector. Now if you calculate, what do you get? x1 times y1 plus x2 times y2 plus x3 times y3 plus, and so on. And more precisely speaking, you're going to end up with a 1 by 1 matrix, but 1 by 1 matrix is just a real number, so we do not use these parenthesis notation there. In short, if you use orthonormal basis, then scalar product computation is exactly the same as the usual dot product computation that we had been doing from, well, long time ago, since trigonometry or even before. Now you may wonder, You may wonder, what's the importance of this orthonormal basis? What if I select different basis system which is not orthonormal? In that case, what kind of expression do I get instead of this simple expression? That question will be answered a bit later in section 2 of this notebook. But before going over there, and also before proving this, let me show you the example of it. An example of it. This is one. There you go. It is possible to define scalar product like this, x star y, where x and y are row expression and column expression, but instead of just straight up computation, we can insert a certain matrix in there, and we get this strange matrix, which always has to be symmetric, by the way, and that is associated to the selection of the basis. So if we have orthonormal basis, then the matrix that goes in the middle becomes extremely simple. It'll become just identity. So you get just this times that. And then in the middle, we have just identity matrix, so no change. But if you have coordinate expression with respect to not these, but something else that is not orthonormal, in that case, you may have some matrix inserted in the middle here. What kind of matrix that is, that's something we are going to be answering in section 2 of this notebook. For now, let's concentrate upon the proof of this. Okay, let's prove it. And the proof is not difficult, but it can be a little bit confusing because of the indices. Ready? Okay, here we go. So V comma W, and V is associated to coordinate matrix X, and W is associated to coordinate matrix Y with respect to the basis system, U1, U2, U3, U4, and so on. So this is what we get. X1, U1 plus X2, U2 plus dot 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 Xn, Un, which is highlighted in blue, and similar linear combination highlighted in red. Now, you can use the bilinearity. We can decompose all those linear combinations here in the first coordinate using the bilinearity applied to the first coordinate. So x1 out, and x2 out, x3 out, all the way over to xn out. And then the right hand side, the second vector does not change. Now, for each vector here, we can now decompose the right hand side, the second vector. First vector u1 stays the same, u1 stays the same, and x1 is just coefficients, so they all stay the same, please note that. And then this linear combination, you can decompose y1 u1 plus y2 u2 plus all the way over to yn un, and that's what this first expression is all about. Is everybody following? And here, please note that u1 u1 is 1 because this is a normal vector. Orthonormal basis, so it's a unit vector. And everything else, u1 u2, u1 u3, u1 u4, all the way over to un un, they're going to be all zeros. You see? The first one, alright, x1, y1, everything else is going to be 0. Because this dot product, next dot product, the last scalar product, they're all zeros. And then repeat the same thing, repeat the same thing. For example, what if you do the last one over here? Same deal. Xn stay the same, un stay the same. Yes, they all stay the same. And decompose those y1 u1 plus y2 u2 and so on, like this. And then what do you get? This is 1, un comma un, that's 1. And all other scalar product, they're all zeros. All zeros. Because we are dealing with orthonormal basis. So what do you get? x1, y1 from the first multiplication, x2, y2 from the second multiplication, x3, y3 from the third multiplication, and so on and so forth, all the way over to x and yn. And sum of all that, that's precisely what we wanted. Okay, it's not a difficult proof. All we did was just applying the bilinearity to the first vector and then to the second vector, as I color-coded, blue first and red later, and then just observing a bunch of zeros. But it can be a little bit confusing because of so many dots. Here's another proof, but this time, instead of dots, I'm using the sigma notation. And this is less confusing if you have more experience in sigma notation. If you don't have enough experience in sigma notation, then this may not make much sense. But then again, this is 3000 level course, so even if you're not really too much into those sigma notation, now it's a good time to learn it, so let's begin. So we can write those linear combination as blue and red like this. Like this. Okay, and then that's blue. We can decompose all those out. And then that part stay the same. Now for each xi and then ui, we can decompose this second sigma notation. So all the yj's out, and then we get this uj. It's a big summation. And then ui dot uj, that's 0. 0 all the way, except I and j are the same. In that case, it's 1. So when I and j are different, they're all gone. Only when I and j are the same, so I don't have to consider two sigmas. I is just running from 1 to n, and j is equal to I. Only that case will survive. And you're going to get, oh, excuse me, this should be yi now, because j is equal to I now. xi, yi, I don't need new picture, so leave it as black. And that one all go down to 0, except when I and j are the same, in that case 1. So what did you end up with? Summation of xi, yi's. That's precisely what we wanted. So compared with this, we have much shorter proof and less confusing. The less dots, the less confusion. So it's better. Now, the downside may be you have to be good at this sigma notation, but that's something you'll have to accomplish anyway. So here we go. Okay, the conclusion. We can calculate the scalar product using the straight ahead dot product expression, exactly same as that. This one. Or in a little bit more elegant fashion, x transpose times y using matrix expression. If, big if, you have orthogonal basis system and coordinate vectors associated to this orthonormal basis system. Okay, now that we have this, let's consider a corollary, and I don't know whether this can be called corollaries or it is going to be a separate theorem, I don't know, because in terms of proof it's really simple, but in terms of implication it's important enough. Anyway, it goes like this. excuse me, let me call theorem. Okay. I mean, theorem is something big, and the corollary is something that just follows from the previous theorem. And the lemma is preparation for some theorem, and so on and so forth. And proposition is even less important. But this one, I originally called it as corollary because technically it just follows directly from this. But on second thought, the proof may be simple, but the implication is something that can stand alone. So let me make it a little bit more formidable here. Okay, let's go to the statement here. Let V be a scalar product space, a vector space with scalar product. And then U1, U2, U3 all the way over to Un is an orthonormal basis. And then let's consider a linear map from V to itself. And linear self-map or linear operator, that's the term our textbook author is using. And whenever you have a linear map, you can consider a matrix associated to that linear map. Okay? And if L is going from Rn to Rm, then A is going to be n by n matrix. For example, if L had been going from R7 to R5, then A is gonna be 5 by 7 matrix. 5 by 7. So it can be a little bit confusing. Is 7 by 5 or 5 by 7? It can be confusing, but not here because this is linear map to itself, so it's square matrix, n by n. No worry. Now that is gonna be the case for probably for the rest of the semester. We're gonna consider mostly square matrices and linear operators only. I may have some exceptions sometime, but at this moment I cannot think of anything. So probably everything major is going to be just square matrix from this point on until the end of the semester. So you don't have to worry too much about it. In short, it's just n by n matrix, square matrix. So you're free to consider its transpose, which is again n by n, and L transpose is a linear map associated to the transpose matrix under, of course, the same basis. So if I do that, then it turns out like this. L of V of W is equal to V, comma, L transpose of W. So I can just move linear map from one coordinate here, coordinate or first vector to the second vector by taking transpose. And then also vice versa, because double transpose is itself. And the proof is, of course, very, very simple. I mean, linear map is nothing more than AX. And as we saw before here, we're simply taking transpose, and then we are just applying transpose operation. X transpose, A transpose. Remember, we have the change of order. And then associativity, A transpose Y, and then we have A transpose Y like this. And you can pass it on the other way as well. So we ended up discussing the calculation method for scalar product given orthonormal basis, and also we talked about transpose operation. We can simply pass on one matrix to from left to right or right to left by taking the transpose. Okay, let's stop here and then we'll discuss the other topics in separate videos.